Hi grade 12s and welcome. Today we're going to be talking about vertical projectile motion and momentum. Let's get started. When I speak about vertical projectile motion, I'm thinking things being thrown up or fired up or projected up in some way and then falling down under the influence of gravity. And momentum, we're going to be talking collisions and explosions. So let's get stuck into the first question, a classic question of a hot air balloon and something being dropped out of this hot air balloon. This was from one of last year's papers. Let's go together. A hot air balloon is moving vertically upwards, so already that balloon is moving vertically upwards at a constant speed. Critical that we know it's going at a constant speed. A camera is accidentally dropped from the balloon at a height of 92.4 meters, as shown in the diagram below. The camera strikes the ground after 6 seconds. Ignore the effects of friction, and there's our picture. So we have a little person with the hot air balloon, and he's dropped something, and it looks like there's someone running from the bottom going to try and catch it. And we'll try and see what that question will tell us a little bit later. Notice the height, 92.4 meters above the ground. The first question. At the instant the camera is dropped, it moves upwards. So the camera is released out of the hot air balloon, it continues to move upwards. Give a reason for this observation. Well, you need to consider that the hot air balloon was going up, and so the camera would have that same initial velocity and be going up as well. Let's have a look at what the memo's answer says to us. The initial velocity, or the speed of the camera, is the same as that of the balloon for your 1 mark. Let's go into some calculations now. 1.2. Calculate the speed, and they tell us the initial speed at which the balloon is rising when the camera was dropped or is dropped. Now, we're going to need to look at equations of motion, and on your data sheet those equations are given to you. But I want us to consider firstly how to choose the right equation of motion and how to solve this problem. Let's have a look at what information we were given and how to approach this problem. Well, firstly I want to ask you always, number one, to choose a direction. By direction, I'm meaning up or down is positive, left or right is positive. In this case, we're looking at vertical motion, so we're going to be considering either up or down as positive. Now, for simplicity, I'm going to choose up as positive. So a little arrow, up is my positive, and therefore down will be my negative value. Once you've done that, you then need to consider every motion that is either up or down, every vector quantity as being positive or negative, depending on what you've chosen for your direction. The next thing we need to do is, and I'm going to write it as my number 2, is write a list. Now by my list, I mean all of the values that I've been given. So this is the list. V final, V initial, acceleration. Maybe we've been given something about time. In this case, yes, we have. Delta X or delta Y, which in this case is my height, that this camera has been dropped, and that should give us a good start. So we've chosen direction, and number 2, we're writing a list. Let's go back and see what the question told us, and we have the camera is accidentally dropped from the balloon at a height of that. So this is the height that the camera is going to fall from, and they tell us that it strikes the ground after 6 seconds. Let's go back and find our list and write in that information. So final velocity I don't have. Initial velocity, that's what I'm trying to find. So I'm going to put a question mark there. They're asking me in this question the speed, the initial speed at which the balloon was rising, and so therefore the camera has as well. The acceleration, well, acceleration is a value I know. It would be the acceleration due to gravity. But notice here we've chosen up as positive, so down is negative, and gravitational acceleration will be pulling this camera down, so that needs to be a negative value. Time was 6 seconds. Time is a scalar quantity, so we don't need to write positive or negative there. It will be fine. And then lastly, the height from which it falls. Again, it's falling down, so 92.4 meters was my value of this fall. If I just sketch it for you very quickly, we can have this picture like that. The hot air balloon was somewhere about here with its hot air balloon with its contents, and the camera dropped out of that. Initially goes up and then falls down. Let's go on and see how we're going to choose the equation of motion, because we need to work with one of those equations. So have a look. Well, we've got information that we know, and we've got information we don't know. I have no knowledge of anything about the final velocity, the speed at which it would hit the ground. I need to know the initial velocity, so that must be in the equation that I'm going to use. I've got acceleration, got time, and got delta x or delta y, the height, the displacement it has fallen. Let's have a look at my equations. Now, I can't use this top equation, the first one, because it's got final velocity. I can't use this one either, final velocity again. I can't use that fourth one, final velocity I don't have. But I can certainly choose to work with this equation, and they give you options there. But what they're saying is that delta x, or we're going to actually be working with this part, delta y, which is y on the, if you imagine that on an axis, the y-axis would be talking about the vertical axis. So delta y is equal to initial velocity times time plus a half a delta t squared. That's the equation I've got information for, and that's the equation I'm going to use. And I've got the final answer written here. Let's just talk about it. Delta y is equal to initial velocity times time plus a half at squared. You will always get a mark for writing that equation. It's given on the data sheet. You need to choose the appropriate equation and then write it down. Make sure you write it down correctly, of course. Plugging in your values, substituting your values. Notice I'm choosing down as negative, or so up as positive. So the height, it's fallen, is a negative value. Initial velocity times time was 6, plus a half, 9.8, also negative, multiplied by 6 squared. Now, depending on how good your calculator skills are, you can probably just put that in, but I want to advise you that you always work with a square first, because so many students I've seen in the past forget to square the time, and so that is an important thing. You need to remember that that time is squared. And what I do when I work these calculations out is I very often start at the end and then work out the whole term, knowing then that I've taken into consideration that square. So our final answer here, 14 meters per second. They asked us for a speed, so we don't need to give direction. If we did need to give direction, the direction would be up, because the hot air balloon was moving up and then the camera was dropped, so it still had an upward direction. But speed is a scalar, so we can ignore direction. Question number 3. Draw a sketch graph of velocity versus time for the entire motion of the camera. Indicate the following on the graph: the initial velocity and the time that it reaches the ground. So that's a value that I've just calculated from 1.2, and then the time that it reached the ground was my 6 seconds that I had previously been given from the question. Now, when they say a sketch graph, we're referring to a relatively quick graph, not that much detail, but the big detail you have to have on your sketch graph is you need to include the labels on the axes, both labels and units on the axes. So we've got a velocity versus time graph, and your basic idea is that you're going to have velocity in meters per second and time in seconds. Now let's have a look at what this graph would look like. Remember, we said it's got an initial velocity that is positive, that is moving up. And if we have a look now, I've got the graph in front of us. If we have a look, again, I've chosen up as positive. And what you should notice here is that we've already got 14 on the graph. That's a value that I needed to include because they asked me to indicate the initial velocity on the graph. That's a positive number because it was originally moving up. Then we have a look, it goes through 0, we'll talk about that, and continues down for 6 seconds. Have a quick look at, once again, what this picture would look like in reality. So my hot air balloon was somewhere there, and it's my little sketch of the hot air balloon. The camera was released from some point. It has an initial velocity. Okay, it gets to the top of its motion somewhere along here, where at that point its velocity is 0 meters per second, because right at the top of its motion, it's now for a split second going to be 0 meters per second, and then it will continue to fall down and accelerate towards the ground. But recognize that for a moment, and I'm just going to neaten this up here, for just one instant up at the top there, it's going to have 0 velocity. And you can see that on my sketch graph, that at this point over here, velocity is 0. That's very important. That's something that markers would be specifically looking for, that you recognize that this thing has got initial velocity to 0 and then final velocity. And that final velocity, because we've chosen down as negative, will be on the negative part of your graph. Let's continue to the next part of this question. If a jogger who was 10 meters away from point P as shown in the above diagram. Now, let's see. I think I've got the diagram. There it is in front of us. So here we've got a little guy. He happens to be running. He looks up into the sky, and suddenly he sees the camera being dropped from this point up here. Okay? If a jogger 10 meters away, that's a distance or displacement value, from point P as shown in the diagram, running at a constant speed, that's critical as well, that he's going at a constant speed, and they give us the value of 2 meters per second. He sees the camera at the same instant it starts falling. So from that we know the time is the same for both the camera falling and the jogger running. From the instant it starts falling from the balloon, will he be able to catch the camera before it strikes the ground? So will he be able to get there in time to catch this camera? Use a calculation to show how you arrived at your answer. Well, we've got quite a lot of information here, but the basic idea is that he was going at, his velocity was 2 meters per second, right? He's got a distance of 10 meters to cover. Will he get there in time? Well, this goes back to a constant velocity value, okay, 2 meters per second. And coming back, we can have the very simple equation, and I'm going to keep writing in green so you know that it's the jogger's values. Velocity is equal to delta x over delta t, which is distance over time. So we've got the distance, we don't have the time, and that's what I want to work with. Rearranging the equation, solving for t, delta x over velocity is equal to 10 meters divided by 2 meters per second. And will he get there? Well, your math should be good. He gets there in 5 seconds. Will he catch the camera? Well, hopefully, if his ball eye skills are good, he should, because he could get there in time, certainly. He should be able to cover that 10 meters in 5 seconds, and so the camera was only falling in 6 seconds, was only going to reach the ground. So yes, he should be able to catch the camera. The time is less than 6 seconds. I hope that's been helpful for you. we'll stop there and come back with some more questions and some graphs on equations of motion and projectile motion. Welcome back, grade 12s. We're going to continue our looking at vertical projectile motion and specifically some graphs of motion. Let's have a look at this question. The velocity time graph shown below represents the motion of two objects, A and B, released from the same height. Object A is released from rest. They've put it in bold for us because it's in capitals because it's so important. And at the same time, same instant, object B is projected vertically upwards. Ignore the effects of friction. So let's consider this in real life. You've got two objects. One is just dropped, released, and the other one is thrown up at exactly the same time. An example of this could be a coin toss. So one of the coins we just drop, and the other one we flick up into the air at the very same instant. Have a look at what the graph would look like. This, remember, is a velocity time graph. They give us velocity in meters per second and time in seconds. We have object A and we have object B. Object A released from rest. Do you see it's released from 0? And object B released from initial velocity of 20 meters per second. Let's have a look at some questions based on this graph. Object A undergoes a constant acceleration. Give a reason for the statement. So by referring to the graph, no calculations are required. So they're telling us information, but we've got to give a reason for why that information is true. For 2 marks, no calculations are required. Well, if I jump back to the graph, have a look at it. The first thing I want you to notice are those straight lines, and specifically the straight line for object A, which is what they're asking us to consider. Straight line graph, very simply, you should note that for a velocity versus time graph, your acceleration is equal to the gradient. Now, let's just consider what gradient means. It is the change in the vertical or the y-axis divided by the change in the x-axis. And for velocity time graph, velocity is on the y-axis, so that would be change in velocity divided by what's on the x-axis, change in time. And that is exactly the same as acceleration. So because we have the gradient is the constant for a straight line, you know that the acceleration is also constant, and it's actually negative 9.8 if you consider the graph as a negative, and our memo will tell us exactly the same thing. The gradient of the graph is constant, so therefore it must be undergoing a constant acceleration. To the next question, 1.2. At what time or times is the speed of object B equal to 10 meters per second? So, at what time is the speed of object B equal to 10 meters per second? That's going to be reading off this graph, and I have it below. The first one, very simply over there at that time, and we can dot it down at 1 second. So time is equal to 1 second. That's one of the points at which B is at 10 meters per second. But now if I look back, they asked us for the speed, and speed is a scalar. So direction doesn't come into account. And B is also found here at 3 seconds at negative 10 meters per second. But if you consider that this is object B that was projected into the air like flipping a coin, it got to a point where it was 10 meters per second after 1 second, and then as it falls, it gets to 10 meters per second again, although now it's going down. So we have 2 times t is equal to 1 second and t is equal to 3 seconds for this for coin or graph B. 2.3. What is the velocity of object A relative to object B at t is equal to 1 second? Now here we're going to be considering both direction, very important because we're considering the velocity, and relative motion. So A we know, and I'll jump back to my my graph here. A is falling down, B went up and then is falling down. So it went up and now it's falling down. And they asked me at t is equal to 1 second. Let's just check that. Yes, at t is equal to 1 second. Well, go back and read off the graph. At 1 second, B was going up at 10 meters per second, and A was going down at 10 meters per second. So if we consider B's velocity relative to A, it would be, A's velocity, I think it was, they asked us, object A's velocity relative to object B, it would be object B would seem to be going at 20 meters per second, meters per second down, because we're considering A going upwards and B going downwards, and so A would seem to be going down at 20 meters per second. They're moving apart from one another, and so their speeds would be added to one another because they're covering that distance away from one another in the same time. If we consider the next one, 2.4, object A strikes the ground after 4 seconds. This is our time, 4 seconds. Use equations of motion to calculate the height from which the objects were released. So the height is asking me delta x, or in this case, actually because it's a vertical motion, I would rather write delta y. It strikes the ground, use equations of motion to calculate the height from which the objects were released. Let's head down, and once again you're going to go and look at your data sheet and find the equations of motion. Now once more I want to choose direction, and I'm going to shift up just here. My direction, I'm going to say up is positive, down is negative. Then let's write my list. We had t is equal to 4 seconds. T was equal to 4 seconds. We have initial velocity. Now what was the initial velocity? This was for object A. Object A was released from rest, so its initial velocity will be 0 meters per second. We also know that it's going to be under the influence of gravity, so A is something I know as well, 9.8 meters per second squared, because it's an acceleration. Okay, final velocity, I don't have. V final is equal to, I don't have it, so I can't even write it down. What else do I need to know? I need to find delta x, or actually, delta y, because it's our vertical height that this object was released from. Once more, let's look at the equations of motion. I can't use this one because it's got V final. I can't use that one because it's got V final. I can't use that one, it's got V final. I'm going to have to work with this third equation. Delta y is equal to initial velocity times time, which was 4 seconds, plus a half at squared, and I have all those values, so let's plug them in. Delta y is equal to initial velocity times time plus a half at squared. You will always get a mark for writing that equation down, so do choose to write that equation and write it really well. Then substituting your values. Well, our initial velocity is 0, so 0 multiplied by 4, that whole term will fall away, that whole part of the equation will fall away, plus a half. This this memo has actually given the acceleration as 10 meters per second down. That's okay, and time is 4 seconds. If you had used 9.8 meters per second, per second squared, you would come out with a final answer of 78.4 meters. I'm just going to do another quick substitution over here. Notice if I had chosen, remember I said I chose down as negative, so initial velocity, I'm just going to write there naught because I know what that is, plus a half negative 9.8 times the 4 seconds squared. It will come out with a negative value, negative 78.4 meters. I would never leave my answer as a negative. You would always want to interpret what that negative meant. So in your final answer, you would write 78.4 meters down. And that answers the height from which the object was released. It's fallen a distance of 78.4 meters down. If we move to the next question, what physical quantity is represented by the area between the graph and the time axis for each of the graphs A and B? Well, this is a good question. It's asking specifically for the area under a graph, and the area for, once again, a velocity versus time graph, meters per second, time in seconds, is always going to give you, and I'm going to just shade this a little bit in here, that whole area is going to be a length times a breadth. And the length would be the time and the breadth would be the velocity. So actually what you're working with here is velocity multiplied by time, which will give you delta x, or your displacement. I want you to show that to you mathematically, because, and it's true for whether it's a rectangular shape or whether it's a triangular shape, the area under a graph for a velocity versus time graph will always give you the displacement. Now you do need to take into account whether it's going in the positive direction or the negative direction, whether it's above the line, the zero line, or below the line. Let's have a quick look at the bottom, and we have got here our answer for what physical quantity is represented. It is the displacement or the change in position. They will also accept distance, the distance covered. Calculate without using equations of motion. Now they're being specific here. They are guiding you towards answering this based on the information on the graph. Calculate without using equations of motion the distance between object A and B at t is equal to 1 second. Now, if I have a quick look here, from t is equal to 1 second, A and B are on going at quite different speeds, and the one, remember, was going up and the other was going down. So have a look here. B is still going up because it's still got a positive velocity, and the A is falling down at getting to a maximum of 10 meters, negative 10 meters per second squared. Now, I want to work out the area of this shape. And it's quite a tricky shape to work with. Some of you might be able to do it, but I'm going to split this up and treat it in 3 parts. Part number 1, part number 2, and part number 3. Okay? So if we scroll down, have that picture in your mind. Part number 1 is going to be looking at half base times height, because that's my first area right at the top there. Okay? It's a triangular shape, and the area of a triangle, half base times height, is equal to, and it's a half times by 1 times by 10, going up, check those, 1 second, the base, the height of 10 units up on the graph, and so half base times height is equal to, well, a half of half times 10 will give me to the 5 meters. Point number 2, or area number 2 I should say, is this rectangular area here, and we have, that's just going to be a length times breadth, which would be giving me 1 times 10, which is 10 meters. Both of those values were for B, which was going up. The last little area I need to work with, area 3, again, half base times height is equal to a half the base of 1, the height of 10, base times height. And so again you have 5 meters, but in this case we're looking at A, and it was falling down. So it is going down. If we head back to over here, the memo has gone through a number of different things, but have a look here. What we've got is that we've got the distance covered by B, and we've worked out the 10 and the 5 and the 10, giving us 15 meters. That object B has gone up. Object A, on the other hand, that was object B, so that was my first part, this was my second part, went down by 5 meters. And do you recognize that they have found the negative? Again, you could work with this because you would have gone negative for your height reading off the graph. Gets to a negative 5 meters. What that means, we're looking now at the difference between them. A has gone up, B has gone down. So when you add them, you're actually working out the difference, and the direction comes into play, and you would say the difference between them is 20 meters. 15 up minus the 5 negative down is going to give me my total of total of 20 meters difference between those two. And that's the end of question 2. When we come back, we're going to look at relative motion and some momentum questions. So do join me again. Welcome back, grade 12s. We're going to continue this lesson on vertical projectile motion and momentum with another question. This is involving a car chase. A patrol car is moving on a straight horizontal road at a velocity of 10 meters per second east. The same time the thief is in a car ahead of him is driving at a velocity of 40 meters per second. He's speeding in the same direction. Now that's critical. And so here we have our picture, the patrol car and the thief trying to speed away from us. They give us this annotation at the bottom, the velocity of the patrol car relative to the ground and the velocity of the thief's car relative to the ground, and those would relate to those two values. 3.1. Write down the velocity of the thief's car relative to the patrol car. So the thief's car relative to the patrol car. Now I want you to think, without looking at any equations or anything, I want you to think about what the situation would be. The patrol car is going along, the thief's car is going along, it's going faster. So the thief's car is almost getting away. At the moment he's getting away from the patrol car. How would we work this in terms of the numbers? Well, let's work it down. The thief's car is going at 40 meters per second. The patrol car was going at 10 meters per second in the same direction. So what is the difference between those two? It would be negative 10 meters per second is going to get me a difference between them of 30 meters per second. So the patrol car would see the thief's car getting away, if you like, at 30 meters per second faster than what he's going at. We do need to notice that this is a velocity, so you need to give a direction, and they gave us the direction in the original question. It was moving east and he was going in the same direction. So our final answer here must include direction. 3.2. A person in a patrol car fires a bullet at the thief's car. The bullet leaves the gun with an initial horizontal velocity of 100 meters per second relative to the patrol car. Ignore the effects of friction. Write down the initial velocity of the bullet relative to the thief's car. So we have values there, that is relative to the patrol car. And the way we're going to work this is we're going to consider firstly, and ignore the top part, that's my final answer, but this is the velocity of the bullet, firstly relative to the ground. It was going at 100 meters per second relative to the car, the patrol car that it was shot out of, with an extra thought that the car itself was moving at 10 meters per second. So the bullet to the ground is going at 110 meters in every second, or per second. What about the bullet to the thief's car? This is now taking it further to actually answer the question. Well, the bullet to the ground was 110. We've just worked that out, going at 100 meters, with including the extra 10 from the patrol car. And we know that the ground to the thief was going at the velocity of the ground, the thief relative to the ground, or the ground relative to the thief, was 40 meters per second. Once again, they're going in the same direction. The bullet's being fired and the patrol car is moving off at the same direction, and so those would need to be worked out, the difference between the two, and that's why we use a negative value. So again, you come out with your number 70 meters per second in the direction being east. Let's move on now to what else happens in this problem that we have. While traveling at 40 meters per second, the thief is going that speed. The thief's car, with its mass, collides head-on with a truck of mass 5,000 kilograms, moving at 20 meters per second. So we have the truck with its speed of 20 meters per second and the car with its speed of 40 meters per second. Notice they're moving in opposite directions and they collide head on. So the one's going this way, the one's going that way, they're going to be colliding. After the collision, the car and the truck move together. Now that's helpful because it's telling us that their final velocity will be the same. Ignore the effects of friction. State in the law of conservation of linear momentum in words. Momentum, and we're looking at conservation. Now conservation is, we're trying to keep things the same, and so the conservation of momentum is a definition you need to know. I've got it here on the board. The total or the sum of the linear momentum of a system remains constant or is conserved, does not change in an isolated or closed system in the absence of external forces. So the idea is that the total momentum of an isolated system without any external forces remains the same. And that's how we're going to find some information about this collision, because in the collision there are going to be, we're going to be looking at the momentum of each, adding them together, the total momentum. Calculate the velocity of the thief's car immediately after the collision. So once again, we've got velocity, and this is going to be the final velocity of the thief's car. I did say to you at the beginning that they said to us in the question that they move together. So their final velocity for the truck and the car will be the same. Let's just check we've got all the information. While traveling at 40 meters per second, the thief's car with its mass collides head-on with the truck of that mass moving at 20 meters per second. They're colliding head-on. I'm taking this from the previous question that was going east, and this would be going west if they're going in opposite directions. Let's look at how you're going to solve this question. Once again, you need to always choose your direction. vitally important. If you can choose your direction, you can then work out some values will be positive values going in that direction, some values will be negative direction, and so it would be negative values, and it makes a significant difference. I'm going to choose to the right as positive. That's the way I often like to work things. To the right is positive, and conversely, obviously, to the left is going to be a negative. Now, my equation is the sum of the momentum before is equal to the sum of the momentum after. That's the easiest, quickest one to work with. Thereafter, you're going to split it into the mass times the velocity, mass times the velocity for each of the components within our system. So I'm going to write this out. The mass of the car times the initial velocity of the car plus the mass of the truck times the initial velocity of the truck is equal to the mass of the car, the final velocity of the car, which I know is the same as the truck, so I'm just going to leave it at final velocity, the mass of the truck, the final velocity of the truck. Now, because I know those two values are the same, we can actually put this in brackets, mass of the car plus the mass of the truck. They stick together and we can work that out. Be very cautious with your subscripts in these cases. Make sure that you, on the left-hand side, put all your initial velocities, on the right-hand side, all your final velocities, and work with those. So, plugging in our numbers, it was 1,000 multiplied by the initial velocity of the car, which is 40 meters per second to the east or to the right. So I'm using the 40 meters per second as a positive number, plus the mass of the truck was 5,000. The initial velocity of the truck, I need to just jump back and see it, was 20 meters per second in the opposite direction. So notice here, sorry, let's jump down here, it was negative 20 meters per second there. Now I need to rewrite this, but I'm going to rewrite it for 40,000 plus, and actually that's going to be a negative, so let me change that quickly, minus 100,000 is equal to the 1,000 plus the 5,000 V final. Working that out, that's going to give me the 6,000 V final, and this comes to negative 60,000. Divide both sides by 6,000, and you come out with a final velocity as being equal to negative 10 meters per second. The negative value there is very, very important. You cannot leave your answer as negative 10. You need to interpret what that negative means. That means 10 meters per second to the left, because if you recall at the top here, I wrote anything to the in the negative is to the left, or preferably actually in the context of this question, west. Let's just check the memo. See, we've got everything. Notice they've said their sum before is equal to sum after, plugging in the numbers and taking into account that negative. Research has shown that forces greater than 85,000 newtons during collisions may cause fatal injuries. So that's a piece of information that's useful. The collision described above lasts for 0.5 seconds. The 0.5 seconds is our time value for how long this collision took place. Determine by means of a calculation whether or not the collision above could result in a fatal injury. So that's my question. Let's have a look at what information I have. I've been given values for velocity. I've been given values for time. I've been given values for mass. I know both final and initial velocity. So the equation we're going to be working with is force multiplied by the change in time will be equal to the change in momentum, which is the same thing as the change in, the mass multiplied by the change in velocity. Having a look at this, let's rearrange it. Force is equal to, that's what I want to get by itself, is equal to mass, the final velocity minus the initial velocity divided by the change in time. Let's just go back and consider, make sure we've got all our values for velocity. This car was going, it's my little car, was going east at 40 meters per second. Once it had collided with a truck, it is now going negative 10 meters per second. We got that from our previous question, which meant 10 meters per second west. Let's take a look and see how we're going to substitute these values in. The 40 meters per second was my initial velocity, the starting velocity before the collision. The 10 meters per second west was my final velocity. But recall that when I put these values into the equation, they need to be positives and negatives depending on direction. So let's have a look and go back to our equation. The mass was 1,000 kilograms for this car. The final velocity was negative 10 meters per second. The initial velocity was 40 meters per second. But notice you're working out the difference between them. So final minus initial, it is a negative value minus another value. And that was all divided by delta t, which I know is 0.5 seconds. Shifting down slightly, let's solve it, put in the values. That's going to be 1,000 multiplied by negative 50, all divided by 0.5. And it comes out to negative 100,000 newtons. We would never leave our answer as a negative. You would always interpret what that answer means. And so it would be 100,000 newtons to the west is how this force would be experienced. Go back and consider, have we answered the question? No, we haven't, not yet. The question asked us, could this result in a fatal injury? And we compare with the 85,000 newtons up there. The 85,000 newtons during collision may cause fatal injuries. This 100,000 newtons is more than 85,000 newtons. So yes, this could result in a fatal injury. And notice the final answer, you will get a mark for interpreting that and explaining that this collision could be fatal. That's all the time we have for today, but I hope it's been informative and really helpful and that your matric exams will go brilliantly.